meeting, and I will send talks on
In the mail to you.
So, during the last talk, I want to talk about another application of categorically inverted subgroups to the so-called reduced actions of groups or metric spaces. And what I'm going to talk about is joint work. So it's not published yet, it will be published in two joint papers, one with Caroline Apple and David Hume, and another with Caroline Apple and Anna Subramania. So I want to talk about a fairly general question. Suppose you are given a group G and a subgroup H and G. And suppose you are given an action of H on some metric space. Is it possible to extend this action of H to another action of G to an action of G on possibly different metric space? So this is similar to the setup which you have in the representation theory when you define the induced representation. You are given a representation of a subgroup and you want to extend it to a representation of the whole group on possibly larger vector space, right? So my first goal will be to explain how to make this problem precise, how to formalize it in the settings of geometric group theory. Then I'll explain that unlike in the case of representation theory, in our situation it's not always solvable. And then I'll explain that it is solvable if H is hyperbolically embedded in G. And this has some consequences this can be applied to prove something about asymmetrically hyperbolic groups, and that will be the last thing I'll be talking about. Okay, so that's the plan now. Let's try to think what should be the right definition of an extension of a group action in the settings of geometric group theory. So here is my definition. So again, let me remind you that whenever I say an action of a group on a metric space, what I really mean is an action by isometries. All actions are isometric by default. So an action of G on a metric space, so H is a subgroup of G throughout the talk. An action of G on a metric space R is called an extension of an action of H on a metric space S if, well, I could request that S sits inside R, S is H invariant with respect to this action, and the action is the same. Some diagram is commuted. That's not quite what we want in geometric group theory, because we don't really want to concentrate on small scale. We want to think about large scale features. So instead of isometric embedding, I have to request that something is a quasi-isometric embedding, right? And then commutativity of the diagram should be considered up to some epsilon. So what's the proper definition of that? If there exists a coarsely H equivariant quasi-isometric embedding, let's call it F from S to R. That is, so what does it mean to be coarsely H equivariant? For every S in S, if you take the supremum over all H in H of the distances in R between F of GS and G times F of S, that's finite. So this is my definition of coarsely H equivariant. Well, H equivariant means that this distance is 0, right? F of GS equals GF of S. That means that the map is H equivariant. Thanks. So if this supremum was 0, then this H equivariant. I just require that this is finite. And second, what it means to be a QI embedding, that means that there exists some constant C such that for every x, y in S, the distance in R between the images of x and y satisfies the inequality. It's at most, at most C times the distance in S between x and y plus C, and at least 1 over C, the distance in S between x and y minus.
So for one, that C can depend on the point in S?
Yes,
Have different spring
I don't require any uniformity. So here is an example which clarifies the situation. So if H on S has bounded orbits, then, well, from the point of view of geometric group theory, this is a trivial action. The trivial action of G on the point, on S, is an extension. Trivial. Okay? So why is it is an extension? Because the identity map from S to S is a QI embedding, and it satisfies this condition, but not uniformly, because the orbits of H on S may not be uniformly bounded. Nevertheless, I want this to be an extension. Because from my point of view, it doesn't matter whether orbits are uniformly bounded or not, it's just a trivial action from the geometric group theory point of view. So now, the question I want to talk about is the following, let's call it extension problem. Given the subgroup H of the group G and an action of H on a metric space S, does there exist an extension of this action to an action of G in the sense described above? So given a group and the subgroup and given an action of the subgroup, does there exist some construction which, like the induced representation construction, solves the extension problem? In general, it turns out that in general there is no such a construction, and I'll explain why. But then I'll show that nevertheless there is a construction which is similar to the construction of the induced representation morally, and we call it induced action, which does solve this problem in case H is hyperbolically embedded in H. So I will say that the extension problem, which I'll abbreviate as EP, is solvable for the pair H inside G if the answer to the above question is yes, for all actions of H on metric spaces. No restrictions on metric spaces. Geodesic, non-geodesic, connected, disconnected. We consider all possible actions. So, well, first of all, why not always this extension problem is solvable? Here is another extreme example. So let's take G to be the symmetric group on natural numbers. That's the full symmetric group, which includes all permutations, not necessarily with finite support, so it's an uncountable group. Then every countable group embeds into G, that's okay, it's even, right? But every action of G on a metric space has bounded orbits. That's a very interesting property of the symmetric group. It's non-trivial, but it's known. It's not our result, it was known before. I think it was first observed by Yves de Cornelier, and it's based on another result by Bergman about generating sets of this group. But that's a fact. Every action of this group on a metric space has bounded orbits. Now, let's take H to be any group which is, say, infinite. Well, say that's Z. Take the action of Z on R by translations. This action has unbounded orbits, right? Therefore, it cannot be extended to an action on G. Because if you have such an extension, and where is the definition of extension? Here. And G has bounded orbits on R. It follows from the definition that H also has bounded orbits on S. Because having bounded or unbounded orbits is invariant under maps which are coarsely H equivariant quasi-symmetric indexes. Right? So in this case, no non-trivial action, no action with unbounded orbits can be extended. Well, you will not like this example because this is an uncountable group. So what if we want a countable group? Well, if you want to think about countable groups, let me first give you a lemma which will allow me to give you a nice countable example. Suppose that G is a group which is generated by a finite set X. Then for every action of G on some metric space R, the map, the orbit map, which maps an element G of my group to GS, sorry, GR, where R is a fixed point of my space, is a Lipschitz map from G equipped with the metric with respect to the generating set X, standard for metric, to S. Well, this is one of the steps in the proof of, in the standard proof of the Schwarz-Millman lemma and the exercise. That's not difficult. So now with this lemma in hands, I can give you another example. Let's take G to be the bound flux solitary group generated by AB, and the relation is B inverse AB equals A squared. And let me take H to be the subgroup generated by A. So H is isomorphic to Z. So it acts on real numbers by translation. A maps X to X plus 1. Okay, translation action. I claim that this action does not extend to the action, to an action of the code Y. So this does not extend. Suppose it does. So suppose it does extend to an action of G on some metric space R, and F from R to the other R, this is bold R, this is real R, is as in the definition of the extension. Okay, so let's try to think about the distance in R. Well, we fix some point x, well, let's take little r in R, and let's think about the distance in R between the element, the point R, and the point a to the 2 to the n R. Well, on the one hand, let's take R a real number, and this will be f of R, and this will be f of R. This notation is slightly better. So on the one hand, because this map F is a quasi-isometric embedding, well, because it's almost H equivariant, it will be, let's try to describe f of a to the 2 to the n R. So because f is a quasi-isometric embedding, this is at most, at least, 1 over c distance in real numbers between R and a to the 2 to the n R. And remember, minus c. R acts by translations, so this distance is 2 to the n. So this is equal to 2 to the n over c minus, so it grows exponentially. On the other hand, this distance is less than or equal than the distance between f of R and a to the 2 to the n f of R plus some other constant c prime, where c prime measures this h, almost h equivariance, right? Here I use almost h equivariance, which is at most, because this orbit map is a Lipschitz map, it's at most some c prime prime, where c prime prime is the Lipschitz constant from this lemma, times the distance in R, times the distance, well, times the length of a to the 2 to the n with respect to the generating set AB. So I apply this lemma to the generating set x equals a plus c prime. Well, but what is the length of this element with respect to A and B? Well, it's linear, because you have a to the 2 to the n equals b to the negative n, a b to the n, so it's at most 2n plus 1. This is at most c prime prime times 2n plus 1 plus c prime. So what we have a lower exponential bound and upper linear bound, which contradict each other, provided n is big enough. If you think about this example a little bit, you will realize that the obstacle here is actually that h is distorted here, right? So the necessary condition for the extension to exist is that, at least in case of finitely generated groups, is that h is undistorted, and you can actually prove the following proposition. If, kind of extending this idea, if G is finitely generated and the extension problem is solvable for pair H inside G, for some subgroup H, then H is finitely generated and undistorted finitely generated and undistorted is a necessary condition. It's not sufficient. The simplest counterexample is this. Let's take, that's example 3. Let's take G to be the free group, AB, extended by an involution. So T squared equals 1 and T conjugates A to B. And let's take H to be the subgroup generated by K. So again, we take the action of H on the real numbers by translation. A maps X to X plus 1. H will be the free subgroup generated by A and B. And the action of H on R will be the following. A acts by translations and B acts trivially. So this action does not extend. It doesn't extend because if it extends, then in the extension of this action, in G, A and B become conjugated. Now if you have any action of a group in a metric space and two conjugate elements, if one element has bounded orbits, then the other element has bounded orbits, right? However, here, A has bounded orbits, while B has unbounded orbits. So there is no extension of this action to an action of G. On the other hand, in this situation, you can see that H is of finite index in G. So it's of course finitely generated and undistorted. Well, that gives you another restriction which is not clear how to formalize. You can say, well, H must be almost malnormal or something like that, but that's not true. There are lots of actions of subgroups which are not almost malnormal, which nevertheless extend. For example, the simplest situation is example number 4. If H is a retract of G, just algebraic retract in the algebraic sense. So there is a homomorphism from from G onto H, which is identical on H. Then the extension problem for H in G is solvable. In particular, H is not necessarily malnormal here because, for example, every direct factor is a retract. Well, the proof is very easy. If rho from G to H is a retraction, we define and H acts on some metric space S, we define an action of the whole group on the same metric space S by just factoring through the action of H. So for every G in G, we define the action of G on a point S from S to V. So GS is just rho of GS. Now, G is from G, but rho of G is from H. So right side is already well defined. And then it's fairly easy to see that the identity map from S to S is actually an isometric and H equivariant map from S to S. Right? Isometric is obvious and H equivariant because this is a retraction, so its distinction on the H is the identity. So the question is now how to describe the most general situation in which the extension problem is solvable, and the following theorem is proved in our paper with David Hume. First, David Hume. So what we prove is that if H is hyperbolically embedded in G, then the extension problem is always solvable. let me give you an idea of how do we construct an action of the whole group. Well, that's not a real proof. So, suppose that H is hyperbolically embedded into G with respect to some generating set X. So we take the K-graph, gamma of G with respect to X union H, which we know is hyperbolic. And now in this K-graph we have cosets, so this is gamma sub H. That's the subgraph corresponding to H. And we have some cosets, say G, gamma sub H, and so on. And we also have an action of H on some metric space. So this is my metric space S. So now I fix a base point in my metric space, let's call it B. And I take this metric space and glue a copy of this metric space to each coset. So basically, what I do, I take a copy of S here, I take a copy of S here, and then you can either glue them directly, well, up to some little modifications, or you just can do the following. So you take element 1 here, you take base point here, connect them by an edge, and then you do this in an H equivariant way along this coset. So a point H here gets connected to the point HB here, and then you can see it. And similarly here. So you do this construction, and now the claim is that under the condition of the theorem, the nature of map from S to one of these copies of S, to any of these copies, say to this one, is an H equivariant, almost H, well, coarsely H equivariant quasi-isometric embedding. Why? Well, the fact that it is H equivariant is direct, is obvious from the construction, because we do this gluing in an H equivariant way. So it's even H equivariant, you don't need force. The fact that it is a quasi-isometric embedding is a little bit more difficult, because if you glue just one copy of S, that's okay. Now by gluing other copies of S, you can distort the metric in the first glued copy. And this is what happens in all these counterexamples. However, it turns out that if H is hyperbolically embedded into G, these different cosets, they are kind of